outputs is gravity at each of those points. So you pick me a point, plug it into some function, it's going to spit out the gravity at that point. Understand? I hope that makes sense. Another one would be temperature. Just think about the temperature in a room, right? The temperature in this room. Of course, if you look on the wall, there's a thermostat. But if we have a very precise instrument for measuring temperature, the temperature right here at this point is different than the temperature right here at this point, right? And so you could have the input is anything in this room, any point in this room, and the output is the temperature at that point. So you would have this function that takes in where you are and spits out the temperature at that. So these are actually very useful functions where your input's 3 variables. Okay. We're done with that one? Obviously, I don't have a picture of that function. All right, so your homework assignment. These are the homework assignments that I do want you to do. I have not put out the assignments for Chapter 11 yet on our website. So let's just go off of these. I'll write them on the board to the side so you have them. Page 623, 1 through 12. And I put try the range. If you get hung up on range, don't worry too much about it. Moving on to 11.2. Well, if we're going to start talking about functions, then we're going to go back to Cal 1 again, and we're going to talk about limits, right? So, I mean, do you get that there's kind of a theme here? We started this out, we started talking about vectors, but then we said, hey, look, there's these things called vector functions, right? What do vector functions of one variable draw? So, like, what did the vector function r of t draw? Sometimes a line. Curves, right? Vector functions like r of t would draw a curve. Right? That might be in 2 space or in 3 space. Now we just talked about, all right, z is, oh wait, and when we did this, didn't we talk about derivatives, right? We talked about limits, we talked about derivatives, we talked about integrals, didn't we? Now what we're doing is we're looking at z as some function of 2 variables. We're saying that's a surface. And so this is a function, it's a surface. What might come naturally now is, okay, well, let's talk about limits and continuity and derivatives and integrals of these, right? And what do they mean? That's where we're going. So the first thing is the limit. So for the limit, this is tricky. Remember from Cal 1 the definition of a limit. Remember this notation? Limit x goes to a of f of x equals a meant that as x got closer to a, the function got closer to L. So a picture of this is this right here. So here's some function. And what I'm going to do is I'm going to let my x values get closer to 0. So here I go. Notice the points on the graph, right? As my function gets closer, the x values get closer to 0. What is the function approaching? 1. Ah, shit. What happened? Well, because here's the function. The function is actually sine of x over x. Is it defined at 0? No, you can't plug 0 into this, can you? But the limit as you approach 0 is defined. It's getting closer to 1, obviously. We just can't actually let it go to 1, then the computer freaks out, right? So the limit was all about what was happening as you were getting close to a point. It had nothing to do with what was happening at the point, right? How is this going to work with a surface? Here's another example. Another function as we approach 0 from both sides. Look, if we come in from the left, what's my function approaching? 1. As we come in from the right, what is the function approaching? 0. See, so from the left side and from the right side, 2 different values. What would we say in this case? It's discontinuous. We'd say the limit does not exist, right? So what we needed in Cal 1 for the limit to exist is that from the left and the right, they had to go towards the same place, right? It was okay, for the limit, it was okay to have a hole as long as they both went to the same place, yes? But you had to check both from the left and the right, didn't you? All right, well, doesn't seem so bad. Important thing in two-dimensional space, the important thing was that the limit had to exist from both sides, all right? That was the main thing. Now, here's the actual notation that we use for limits with functions of two variables. See, when you were in a limit in Cal 1, x was approaching something, right? You were just approaching along the x-axis. But now, our function is a function of two variables. So your input is actually an ordered pair. So you want that ordered pair to be approaching another ordered pair. Try and illustrate it. Cal 1, you have y as a function of x. The domain in Cal 1 was one-dimensional, wasn't it, the domain? And so if I draw you this, and I say, hey, everyone, get closer to A, then you would come in from this side or this side, right? This is the domain. Yeah? That's Cal 1. What we're talking about now, Cal 3, is that this is the domain, right? You're in two-dimensional space. And now approach a point for me. That point right there, I'm going to call it AB. Approach that point and tell me what the function's doing above that. What's going to be the problem? Does anyone see the problem? I wonder if anyone can see it ahead of time here. Which way are you going to approach it, right? With this one right here, there's only two ways to approach this point, right? From the left or from the right. How many different ways can I approach this point? Infinitely many ways. Look, could I come in like this? I could come in along this line, all these points right there, and that would approach that point, wouldn't it? And then I could do this and say, yeah, I'll do a little curve action and then go towards that point. I could do that. Why not? I could come in and curl through like this, right, and approach that point like that. I could do something crazy. I could start like almost like this death spiral into it, like, right, and just head into it. There's no longer just two ways to approach the point like there was in Cal 1. And that is a huge problem. Because for the limit to exist, you have to be able to show that it's approaching the function is approaching an L from every possible direction in every possible path, which you can never do. Do you understand that? You can never check every path. You don't have enough time in your life to do that. Now, there is going to be some workaround to it, but I just want you to see the inherent problem that we run into when it comes to functions of two variables. That's a notation. All right, let's move on. I'm probably going to reiterate exactly what I just said here. Big questions, how many ways can we approach it? So I think I just showed you, here's a point I can approach it, right? I can come in any way and see what's happening on the function, right? This is my domain on the ground. This is the function. I can come into that point so many different ways that imagine that on the surface, you're just kind of approaching that point on the surface from all these different directions. Infinite number of ways that we can approach it. For the limit to exist, must exist for every path, and therefore our life's going to suck. All right, so let's try this. We are going to investigate this function. This is my actual function of x right here. And I want to know what the limit is as xy approaches 0, 0. And I'm going to look at several different paths. So we have a couple of paths that we like to always try first. And we're hoping for the best. But let's be clear. If I come in and I do a limit right now and I get an answer of 1, that does not mean the answer is 1. to the problem. That means from one direction it was 1. Then I would have to check every other direction, which is impossible. So what do you think it is that I'm actually going to hope for? Going to hope that from different paths I get different answers, right? If I get different answers from different paths, the limit does not exist. So it's easier for us to check that a limit doesn't exist than it is for us to check that it does. What we don't want to happen here is keep on getting the same answer every time we come in from different paths. Because every time we do, all it does is just tells us we need another path, and we're never going to run out of paths. So let's try one of the first paths that you'll want to come in on. Remember, I'm in two-dimensional space. What point am I approaching? I'm approaching the point 0, 0, which is right here. Right? I'm approaching 0, 0. And one path we really like is the x-axis. Like back in Cal 1. Let's come in along the left and right-hand sides like this. Okay, so we're going to come in like this. That's a path, isn't it? And that line that I'm coming in on is actually the line y equals 0, right? Which is the x-axis. Right? So what I'm going to do is I'm going to go to this limit and I'm going to fix my y value at 0. Not approaching 0. I'm going to fix y to be 0. And I'm going to rewrite this limit. So here's what it'll look like. Limit as x0 approaches 0, 0. Notice I replaced the y with 0. And then everywhere in here I'm going to replace y with 0. So x squared minus 0 squared over x squared plus 0 squared. Which equals limit x0 approaches 0, 0 of, well, that's just x squared over x squared, right? And what's x squared over x squared? That's going to be 1, right? That's 1. I can reduce this before I take the limit. So this is just going to be, I'll write it one more time. Limit as x0 approaches 0, 0 of 1. And what's the limit of a constant? Just the constant. So we get 1. Okay, so what appears to be happening is that if I were to be looking on the ground and looking at the x-axis and coming in like this, right? Then up on the function, I should be up approaching 1, shouldn't I? Up on the surface. It should be approaching a height of 1. Now, I'm going to show you a picture of all this in a second, but I want you to kind of see it, try and see it mentally before I show it to you visually. All right, so that's 1. Now let's try a different path. Let's try along, how about the y-axis? That seemed like a natural choice for the next one? Come in this way? Okay, so now let's go along the y-axis, which is the equation x equals 0, and do my limit. This time I'm replacing x with 0. So it's 0y instead of xy. And then replace all my x's with 0, which gives you negative y squared over y squared, which is negative 1. Right? Which means at this point I can stop and I can say this limit doesn't exist. Because from two different paths, I was approaching two different values. Understand that? We got lucky. That's the first example. So limit does not exist. That's the conclusion of this. Question, yes?
So from each path we take, we have to have the same answer? Limit has to be the same, right?
If the limit is going to exist, then we need to get 1 here and 1 here for every path you can ever come up with, which, again, is impossible. So we're hoping that through different paths, eventually we get them to be something different. If we just keep on getting 1, 1, 1, 1, 1, you're just going to be like, I got to find the path that's going to screw it up, but maybe it is 1. But you can't check every possible. So you're really kind of backed into a corner here. Do you see that? All right, so let's take a look at the visual of this. See if you can make sense out of this visual. Okay. All right, this is along the x-axis. So what I'm going to do is I'm going to take the surface out completely, just so you can see what's happening. If you look at it from this side, well, I guess this is okay. Along the x-axis, see that green dot? Yes? The green dot is just the input, and the black dot is actually the output of the function. So do you see as the x value changes, do you see that the z value, I'm sorry, the x value moves along. Do you see that the z value is just staying up there at 1? Something happened there. Do y'all see my computer freaked out there for a second? Right there when I went through the origin, what happened? It tried to plug in the point 0, 0. But you can't, because 0, 0 into this is going to be undefined, right? But if you're getting closer and closer, it looks like that output is 1, isn't it? Do y'all see that? I'm going to come in and bring that surface back in. There's something really weird happening in there. Do you see that little dip in there? Okay? So it looks like from the side, it's almost like a fortune cookie, right? Or something. It's like folded across the top, and you're running along that top edge, and then all of a sudden, at the origin, it drops down, right? It actually becomes undefined. It doesn't drop down, just is undefined. But along that x-axis, it's up there at 1. Understand? No questions? Okay, now let's look along the y-axis. We come in along the y-axis. See, now we're along the y-axis. The green is the input. The black is the output. Notice that the black is below it, isn't it? So it's down there at -1. There's that surface. We were coming along this edge, right? Now we're down along this bottom edge down here. Did y'all see it or not? Give me some feedback. Yes? You see it? Okay. So as soon as we had different answers, we were good. So the conclusion is that this limit does not exist, since we got different answers from different paths. Now let's take this path, or this new limit. So let's go back to our kind of always proceed this way. Always start with maybe the x-axis, then go to y-axis. Okay, if I'm going to go along the x-axis, I'm going to let y be 0 first, right? This limit's going to be the limit as x0 approaches 0, 0 of, now replace y with 0 in there. And what do you get? On the top you get 0, right? Over what? X squared. Now, are we saying here that this top is approaching 0, or are we saying that the top is 0? Is 0, right? Because I am actually sitting here saying, let y be 0 so that I'm on the x-axis, not near it, on it, right? If I'm on the x-axis, y is exactly 0, and then the top is not approaching, it actually is 0. And then 0, the number 0 divided by any number would be what?
0.
It should be 0 as long as this is what? Not 0. But what are we doing? We're letting x approach 0 without actually getting there, right? So these numbers down here are getting smaller and smaller and smaller and smaller and smaller, never actually being 0, so we never actually have division by 0. So the answer to this is 0. Now, similarly, if we come in along the y-axis, let x be 0, do you all see what's going to happen? You're going to get 0 again. But 0 over what this time? Y squared. You get the same answer. So does that mean that the limit is 0? No. It means that along those two paths, the same thing's happening. So what should we try next? Or what should we do next?
Are we going to do a different path?
Yeah, let's do a different path. What do you want to try?
Y
Y
equals -x.
equals -x. That's a good path. The one that we usually go to next is the diagonal. which negative x might also, it's another diagonal. But let's go with y equals x as our next choice. So we're going to approach 0, 0 along the diagonal. So that'll be y equals x. We call that the identity function. That's called the identity function, back from college algebra. So let's approach along the identity and see what happens. So what I'm going to do is I'm going to replace all my y's with x's. And I'm going to rewrite the limit up here. Limit, not instead of x, y, I'm going to write xx approaches 0, 0 of x times x over x squared plus x squared. So all my y's became x's. What is the top? Top is x squared, so limit xx approaches 0, 0 of x squared over 2x squared, 1/2. Done. This limit doesn't exist. We found a path that made it not happen, right? Understand that? Questions?
So for how long is it?
That's a great question. Until you run out of lead or time. I don't know. Most of the problems on the homework, it's going to happen somewhere in here. But there are some more unnatural choices, which the last example I'm going to do will be a less natural choice. Okay? Sometimes you just have to think about what's happening in here and how you can get things to change by manipulating what x and y are. Okay, good? Let's take a look at this one. This is a function. Do y'all have any idea what this looks like? It's a function that if you come in along the x-axis, it's approaching 0. Along the y-axis, it's approaching 0. But if you come in along the diagonal, the function is approaching the value of 1/2. So is it still a fortune cookie? Let's see. It kind of looks like a fortune cookie still. Right? Y'all see that? So let's come in along the x-axis. There's my x-axis coming in. Notice that we're just running along the edge of this graph. I don't know if y'all can see that. Along the x-axis, we're just kind of, there's this dip in the function. We're just kind of running along this edge, right? And it's our z value is always just constant through that. And then we try and come in on the y-axis. The same thing happens. So here's along the y-axis. We get that same edge effect, running along this edge, always staying constant at 0. On the other side, same thing, right? Look at that from the top, running along the y-axis. But now if we try and come in along that y equals x, there's along y equals x. And you can see pretty obviously that we're up on that top ridge now. So we're up at 1/2. Got it? See, this is where we're at a point in the class, and a lot of it's going to be like this the rest of the way. I'm curious to know, as a student, from a student's perspective, how much of this would make sense without that picture? I wonder. Like, would you see it the same way? I don't know. Or would it just be just a limit, and you're just like, okay, how do we calculate the limit? I don't know. To me, I think the visual is just there to help us see how it's tied to something. It's not just like a limit. Okay, so the answer was does not exist. Okay, last one. You want to try? You want to try and go in along a couple of paths. You're good. How many of you see right away along the x and y axis you get the same answer? Do y'all see that right away from looking at it? Because you have x times y squared on the top, as soon as you let x be 0, the top is 0. If you let y be 0, the top is 0. In both cases, the denominators are either going to be x squared or y to the fourth, depending on what you set. So it's going to be very similar to the last problem, right? Anybody get this? How many of you got to this one, tried y equals x? What happens? What do you get?
1 out of 1.
What does it turn into? This algebraically is really just what? X cubed over x squared plus x to the fourth, right? What can you do with this? You factor out an x squared. So you'll get x squared on top factored out. On the bottom, factor out x squared. You get 1 plus x squared, right? Cancel those out. So what happens here? If x goes to 0, what happens here? You get 0, don't you? You get 0? Does that help you? No, that didn't help. So what next? What's your next path? X equals y squared? Where's that coming from? From magic? X is y squared. So think about this. If this was y squared, then this would be what? Y to the fourth. And if this x squared was y squared, then you're taking y squared and squaring it, which again is y to the fourth. And so you'll have y to the fourth on top over 2y to the fourths, and that'll reduce and become the fraction 1/2. So that you have to just kind of understand what's happening in here, and that'll work. It'll work that way. Do y'all get that? So this path, what was it? X is what? X is y squared. X is y squared. So let me replace that. This limit's going to be limit. Instead of x, I'm going to put what here? Y squared. Y approaches 0, 0. Replace my x with y squared, so y squared times y squared on top over y squared squared plus y to the fourth. Which is essentially y to the fourth over 2y to the fourth, which turns into 1/2, doesn't it? And that's all we need to say it doesn't exist. Now, what does that path look like? Parabola sideways. So if I approach 0, 0 on that path, I get 1/2. But if I approach along the x-axis, it's approaching 0. If I approach along the y-axis, it's approaching 0. If I approach along the diagonal, it's approaching 0. So this ought to be a pretty interesting looking function, right? Does anyone have any questions over that? We're good? I'm going to show you the picture of this one because it's pretty cool. There it is. Look at that top ridge. Can you see that top ridge? Right in there? That top ridge? You're walking along that top ridge, you're up at 1/2. That's that parabola. But if you come in the y-axis or the x-axis, you're down at 0, even along the diagonal. So let's see. There's along the y-axis, it's 0. Along the x-axis, oh, can you see through? You can see through it, can't you? That's through. Now remember, at 0, 0, you have this undefined thing happening. Oh, this is cool. Let me show you this. Part of why I wanted to go through this. You know how we checked just a second ago, we checked y was x, right? Y equals x was one path. There's another path that you can choose that's really kind of, you've heard the term like killing 2 birds with 1 stone. This is killing an infinite number of birds with 1 stone. What I could do is come in on the path y equals mx. So think about this. Y equals mx is going to be a line that goes through the origin, right? If m is 1, then it's this one, isn't it? If m is -1, it's this one. If m is 2, it's this one. If m is 3, it's this one, right? So what I'm going to do is instead of fixing my slope, I'm going to let it be arbitrary. And now I'm going to rewrite that limit again. Limit, I'm replacing y with mx, so it's x mx. I hope you understand we already have the answer to this problem. Do you all get that? Okay, but this is another choice you could do that is pretty powerful when it comes to actually evaluating this. So check this out. I'm replacing my y with what? mx, so it becomes x times mx squared over what? X squared plus mx to the 4th. And the question is, what is this? So I'm going to have to be correct, precise with my notation, I need to rewrite this limit again, right? That's a lot to write, and it's class time. So I'm just going to write, this is all L, okay? I do that when I'm doing the homework problems too, because it's too much writing. So this here, on a test, please write it down, okay? It's not that bad. What is the top here?